Alright, so this is the unit on heat and temperature. So before we get right into some of the word problems, I want to give you a good background on really fundamentally what is heat and temperature from a sort of particle level. So any type of object, can contain heat. And that heat is the source of that heat is really from the internal kinetic energy of all the moving particles that exist within the object. So what ends up happening is all things are made out of particles. And when things are really cold, so theoretically if things are very cold, so at absolute zero, it means all those particles are not moving at all. And as more heat is added to that object, more heat's transferred to that object, what will end up happening is the particles will start moving more. Alright, so they start moving more. And the hotter things get, the more they'll move. Okay, so you have a lot more moving particles bouncing into each other, going off from side to side, bounce, 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 all the way around that particular object. So heat really is the overall amount of kinetic energy that exists within an object. And whereas temperature is what happens where we have the average, is going to be the average kinetic energy at a certain point within that object. So it's very interesting that when we look at this and says what has more heat, an iceberg or a lit match, and interestingly enough the iceberg has more heat because there's a larger number of particles that are moving around, so there's a larger amount of overall kinetic energy, but what ends up happening is at that particular point the average kinetic energy of the match is much higher, which gives it the temperature. Alright, so moving through, getting started on this. So like any of the other physical units that we've looked at, it's a really good idea to talk about, we need some units to describe things. So what we can do is use some units to describe temperature. And what we found is that and water, ice seems to melt or freeze at 0 degrees. So we've established that as being for the temperature scale in terms of Celsius, we've established that as the 0 point. And then because water boils at 100 degrees, we've established 100 degrees on that scale as being the boiling point. So every degree of centigrade is that you're going to have 100 different units or intervals between 0 and 100, and that's what's created the Celsius scale. So those are the intervals of temperature, and so even if you go above 100 degrees or below 0 degrees, the intervals are all going to be the same. Whereas on the Fahrenheit scale, we have a freezing point which takes place at 32 degrees, and then we also have a steam point or a boiling point that takes place at 212 degrees Fahrenheit. And what ends up happening is these are the ice points, so they're not scaled on 0. They really have no rhyme or reason on why those numbers were chosen as a scale. The next important consideration is what is the conversion factor for one interval of a degree Celsius and one interval of a degree Fahrenheit. And what we found is, what we have right here is that there is 9/5 degrees Fahrenheit, or what's better to know that is 1.8 degrees Fahrenheit for every single 1 degrees Celsius. Okay, so that's your conversion factor when you're looking at per degree Fahrenheit versus per degree Celsius. And also you have to take in consideration though as well is how far away is that from the freeze point. Alright? So what we have is our first example of how to convert things. So we're going to take a very common thing, which is going to be your temperature. Human body temperature is usually 98.6 degrees Fahrenheit. And then we're going to say, okay, I want to know what that is in centigrade scale. So the first thing that I have to do is be able to convert and figure out how many degrees am I above the ice point. How many degrees in Fahrenheit am I above the ice point? So what we look at right here, that's the most important part, degrees above the ice point. So in order to do that, we are at 98.6. If the ice point is 32 degrees Fahrenheit, it tells us that we're 66.6 degrees Fahrenheit above the ice point. Now, I can then figure out, because I know the number of degrees above the ice point I can then figure out what is the number of degrees in centigrade above the ice point by multiplying it by my conversion factor. And again, remember the dimensional analysis that the Fahrenheits will cancel out. So if you run the calculation of the math across that, you're going to get your answer of 37 degrees centigrade. And remember, we know that this is the amount of temperature in centigrade above the ice point, and just happens that for the centigrade scale, the ice point is 0 degrees, so our answer is going to be 37 degrees. Next page. So another example of this is instead we're going the other way. So we want to figure out, okay, what is 120? We know what temperature we have in centigrade, minus 20 degrees centigrade. Now we want to figure out the corresponding temperature on the Fahrenheit scale. So same thing we do. We're going to figure out, we know that negative 20 is going to be the degrees below the ice point. All right, so we can take our conversion of 20 degrees and figure out, because we know our conversion factor, and we set things up dimensional analysis so that the centigrades cancel out, multiply across, so that we know that we're 36.0 degrees Fahrenheit above the ice point. Okay, the ice point for centigrade though is 0, but because we're converting to centigrade, we have to take in point what the ice point is, for Fahrenheit, and we are, so if we're 36.0 degrees Fahrenheit below the ice point, then we have to take what our ice point is in Fahrenheit, which is different than centigrade, which is 32.0, take away what we have in minus 36.0 degrees Fahrenheit, so our final answer is minus 4 degrees Fahrenheit. There's one more scale that we need to talk about, and I touched upon it earlier. So if we look at matter, so what we did was we set the Celsius scale as 0 as is at the point at which ice freezes. But more helpful for, rather than deal with a negative scale and a positive scale when we're doing more complicated scientific questions, it's sometimes easier to have a more continuous scale where we actually start 0 at being absolute 0, where for a particular substance there's absolutely no motion, there's no kinetic energy within that particle. So what ends up happening is, what we can do as things, it's the same, what this is called is the Kelvin scale, and it centers at 0 around absolute 0, which is the lowest possible temperature you can ever go, so you can never have any negative Kelvin values, and then set things up as the intervals are the same as the centigrade intervals. So what ends up happening is that we find in this particular scale that the ice point is at 273.15, and again the steam point is going to be 100 degrees Celsius greater than that. So this is how these two can connect with each other. So the actual magnitude of the intervals for Kelvin, degree Kelvin and degree Celsius are the same. It's just they're zeroed on something different. So when you ever want to figure out what the temperature in Kelvin is, it's your temperature equals your temperature in Celsius plus 273. Right?